And okay, so let's start with the molecular orbital theory, which is a very advanced theory, and it covers a lot of things that the Lewis structures cannot explain, which the hybridization we couldn't understand through that. So through the molecular orbital theory, we try to make sense of, you know, the bonding, the covalent bonding very specifically. Okay, so first we're going to look at what is paramagnetism and diamagnetism. Next, we are going to look at the postulates of the molecular orbital theory, then the difference between the atomic theory and the atomic orbitals and the molecular orbitals. Excuse me. Then we'll look at the the linear combination of atomic orbitals, that is LCAO. So that is linear combination of atomic orbitals. Okay, and then we will look at the graphical representation of how the s and the p orbitals, so that's basically the molecular orbitals, are formed. Then the bond order, bond length, bond strength, bond energy, and then the last is the energy diagrams with some examples. Okay, so all of this we will cover today. So first of all, paramagnetism and diamagnetism. So what happened is that in the past, they did these experiments. And this is like, you know, in science, in physics and chemistry, generally, you know, we are just doing all kinds of experiments, which are, you know, just sometimes out of curiosity. And, you know, just like, okay, what is going to happen if we do this? What will happen if we do that? Like that type of thing. So nothing very specific. So this was an experiment going on in which, you know, we had taken a test tube, and inside the test tube, we put some liquid oxygen. Okay, so liquid oxygen is here, and actually liquid oxygen is blue in color. So I'm going to put that specific blue color. Oxygen that you cannot see, but once it's liquefied, condensed, and it's blue color. Okay, so you put the test tube containing, so this is the oxygen in the liquid state. All right, that's fine. Now you take this test tube and you suspend this test tube. You obviously you would need it to hold it to something. So you hold it from the top, and this is one side of a balance. And then the other side of the balance, you have some, you know, some weights put in the balance. So basically, this test tube is suspended in a to a balance, and right here you are going to put the magnets. So one is the north pole of the magnet, and the other is the south pole of the magnet. Okay. Now, this is an electromagnet. In other words, when you pass electricity, only then this thing becomes magnetized. If you don't pass the electricity, then it's, you know, it doesn't work. So you can control, in other words, the magnetic behavior. So what we are trying to do is we want to see, is the liquid oxygen going to get attracted to the magnet or not? And if it does, then what happens? And here we put some very small weights. These are called the atomic weights. So these weights are like really, really tiny bits of weights. Okay. Now this is obviously this is a balance. So this is being held like up from, is being held from some kind of a support. Okay. What we see that in the magnetic field, we would expect the test tube to just slide through. Okay. In the magnetic field, we would expect the test tube containing liquid nitrogen to just pass through, but that doesn't happen. When the magnetic field is present, in that magnetic field, we see that the test tube gets stuck. The test tube is stuck in the magnetic field. So it's going like this, and then like that. So this whole magnetic field is, you know, is playing out like this. So when the magnetic field is turned on, the test tube is just stuck. When you remove the magnetic field, when there's no magnet, then fine, the magnet, just a test tube, comes through the gravity. Why is this happening? So we know that here is oxygen, and the Lewis structure of oxygen looks like this, which means that oxygens, every single electron is paired. So all of the electrons in oxygen atoms are in O2, basically in O2, like every single atom in O2 molecule are paired. So if they're paired, why is oxygen attracted to the magnetic field, is attracted to the magnets? Okay, why is it happening? This attraction can only occur. This is called a paramagnetic behavior. So paramagnetic behavior is when the attraction to the magnetic field occurs. Paramagnetism, magnetism is the attraction to the magnetic field only when there is one unpaired electron. So attraction, wait a minute, attraction to magnetic field when one unpaired electron is present. When one unpaired electron is present. Now, when you look at the Lewis structure of oxygen, you see that this unpaired, there's no unpaired electrons. All the electrons you see are paired. Every single electron. This is paired, lone pair. This is paired, that's another lone pair. This one is paired, that's a lone pair. This one is paired, is a lone pair. And then these guys that are bonded are also paired. Not a single electron is seen which is unpaired. We see all of them are paired. So where is that unpaired electron? You see that? So if the unpaired electron is present, then where is it? In the Lewis structure, we don't see it. So that you need that unpaired electron to be attracted to the magnet. Diamagnetism, on the other hand, diamagnetism, I think it's DI, just DI, MAGNETISM. Diamagnetism occurs when there is no attraction to the magnetic field. Okay, so in other words, there is a repulsion to the magnetic field. So repulsion to magnetic field. Okay. And that happens when all electrons are paired. So ideally, you should see repulsion for oxygen. Now, opposite happens when you take nitrogen. Then they changed it. Say, okay, this was the oxygen's example. Look at nitrogen. Nitrogen, on the other hand, nitrogen, okay, has the Lewis structure, which looks like this, triple bond. So here again, all of them are paired. But in the case of nitrogen, you see that it is diamagnetic. It is not attracted to the magnetic field. So oxygen shows repulsion. No, oxygen is showing attraction. But nitrogen, on the other hand, where every single electron is also paired. This is paired, and these 6 are also paired. But we see repulsion in the case of nitrogen. So in other words, when you put nitrogen in the test tube and you pass it through the electrical field, what do you see? That the nitrogen just, slips, slips through. When you turn on the electrical current, the nitrogen slips through. It's not affected by the magnetic field, but oxygen is. So we don't see, in the case of oxygen, we don't see an unpaired electron. So now comes the question that in oxygen, there is one unpaired electron, okay? And in nitrogen, there is no unpaired electron. So if there is one unpaired electron in oxygen, where is it? So that led us to, so where is that unpaired electron? So that led to the formation of a new, and why one? How many? How did we know that it is only one? It is one that when you take now here's the thing. Why did we put the weights here? Because this weight tells us the force that is experienced by the magnetic field. So let's write this here with this color. So this is the force experienced is measured by the weights actually. So force experienced by a substance in the magnetic field, by oxygen or nitrogen or whatever in magnetic field, is calculated by the weights. So this weight tells us how much of that, how much of that force is. So let us look at this. So that is called a magnetic susceptibility. Magnetic susceptibility, susceptibility. Okay, so this is the force that is experienced by a substance in the magnetic field is calculated as follows. So force experienced by a substance in the magnetic is measured by the weights. So what does that mean? Okay, you take the weight before you put it in the magnetic field. So that is the weight A. So that is the weight going in. Take the weight of the test tube containing oxygen before putting it in the magnetic field. Next, take the weight inside, once it's inside the magnetic field. So that is out. So the weight inside the magnetic field, in the magnetic field, and the weight that is out in the magnetic field and out of the magnetic field. So we see that the weight inside is more magnetic field. So we see that A, that is inside is more weight, outside is less. So we see A minus B, whatever that difference is, that number, that is giving you the number of unpaired electrons. So it's a very delicate, very little change in weight, but there is still a change in weight. But that gives you a clue of how many electrons could be unpaired, number of unpaired electrons. Okay, so The unpaired electrons, as I said, is the magnetism, is paramagnetic character, leads to the paramagnetic character, and the presence of no unpaired electron leads to repulsion, and that is the diamagnetic character. Okay, so now we at least have an idea how many electrons are unpaired, at least based on this. That was a conclusion, right? How? Now you have they made this theory, which is based on, obviously, theories are like a big body of knowledge. So what are so they said, okay, we have been looking at the atomic orbitals. Okay, we have been looking at the atomic orbitals, that the atoms, s orbitals and p orbitals, and s and p orbitals, they overlap. And we did the hybridization, and that explained, the ability of some of the atoms to form more than one type of bonds. Okay, like for example, S can make two bonds, but when S combines, when sulfur combines with other atoms that are more electronegative than sulfur, then sulfur will make 2, 4, and 6 bonds also. Same story with phosphorus. When phosphorus combines with a more electronegative atom, then it can make 5 bonds. Xenon, when it combines with more electronegative atoms, such as fluorine, such as chlorine, such as oxygen, then xenon can make 2, 4, and 6 bonds. So that will be understood, through hybridization. That in hybridization tells us that, oh, there's an internal jumping, and they jump from, P to a D, and so they expand, that whole capability is expanded, and that's a great thing. And so, we got that. But we still were not sure about one thing, that is resonance. Why the double bonds keep moving. So if you look at it, that the Lewis structures, they localize. That is a drawback with the Lewis structures. They localize the electrons. Localization of electrons means like, okay, this is the dot, tells us that, oh, the electron is right here. But reality is it's difficult to find the location of the electron. Like we can only say like, okay, in this region of space, the electron is present. But we don't know whether it is going to exist as a wave, as existing as a particle, that we don't know. But we also cannot say at one point of time exactly the electron was present here in this form. That also we don't know. And when we draw Lewis structures, we say, oh, that dot is that electron. So that totally trashes the entire Lewis structures. But Lewis structures have their own value. They help us understand the connectivity in the bonds, the connectivity in the atoms. So Lewis structures have a value of that, but Lewis structures cannot explain a lot of other things. So particularly resonance. So here's we made this a molecular orbital theory, which, so here we are going to look at now. The next thing is, so this is the first part where we talk about the paramagnetism and diamagnetism. Now comes the postulates, or postulates. Now I'm going to just write down postulates of molecular orbital MO theory. Okay, so I don't have to write down this whole big letter. So, okay, first of all, MO theory gives us insights. MO theory helps us understand, number one, the paramagnetic behavior of oxygen. By default, we should expect oxygen to be diamagnetic. In other words, oxygen should not be attracted to the what is it called, the magnetic field, but oxygen is. So molecular orbital theory shows us the paramagnetic and gives us insights into the paramagnetic behavior of oxygen. Okay, why would oxygen be attracted? First thing. Next is, it also helps us. So molecular orbital theory helps us understand the paramagnetic behavior of certain substances. That's one thing. Where is that one unpaired electron, which we cannot see by the Lewis structures? So next is, it also tells us why some of the atoms, they violate the octet rule. Okay, so we understand, yeah, they move up and the electrons expand, but the violation of the octet rules, you know, why still? Some more insights into that. So it also tells us the energies of electrons in molecules. Okay, so we have been looking at the energies of atoms, energies of electrons in atoms, but energies of electrons in molecules. So this is what we learned here. So we understand that. Next is, it also tells us somewhat of a probable location of electrons. Probable. Problem with the Lewis structures is that they really localize. The Lewis structures, they localize the electrons, but the truth is not that. Electrons cannot be localized. So that's the drawback with the Lewis structures. Lewis structures, they localize. As you can see, localize the electrons. But reality is opposite. So we can only know it's a probability of finding the electron. So that has not gone anywhere. That theory still holds very true. Then we also understand why some substances are good conductors of good conductors of electricity. Okay, why some of them are insulators, why some are, you know, semiconductors? So why would, you know, why? So it just gives us more insights into that. And why some of them are insulators, why they are not going to conduct electricity, why would that happen? So it all relates to, you know, the way the atoms are arranged in the molecules. So it's just much more than the Lewis structures. Lewis structures just give an idea about the, you know, understanding the shapes of the molecules. It goes to them. So now we are just that we talked about the probability of the location of the electrons. So just like there is, just look at this here, just like there is a probability of finding electrons is in the probability of finding electrons is now in the molecular orbital theory, finding electrons is in molecular orbitals. So now there are, it's not like there are atomic orbitals, there are molecular orbitals also. And how do you show these molecular orbitals? According to the Schrodinger's equation, it's the psi function, psi. Next, several things are same as the atomic orbitals. So just like the atomic orbitals have 2 electrons, okay, just like every atomic orbital, and atomic orbital, I'm going to do atomic orbital, just like every atomic orbital, AO, MAC can contain a maximum, okay, a maximum of 2 electrons. So does molecular orbitals also. Okay, so maximum electrons present in the molecular orbitals is also 2, and the spin is also opposite, in paired in opposite spin, paired in opposite, you know, spins. So okay, next is the electronic configuration is still the same even with the molecular orbitals. So electronic configuration is the same, you know, as atomic orbitals and molecular orbitals, that's the same. Okay, then next is the very interesting part. The Lewis structures, in Lewis structures, we are looking at in Lewis structures, we are looking at the particle nature of electrons. So that is why we are localizing it. So particle nature of electrons. But in the molecular orbitals theory, in molecular orbital theory, we look at the wave nature of electrons, wave nature of electrons. Okay. And just as in atomic orbitals, the electrons are quantized. Quantized means energies. They have the energies. Electrons have energies, right? So just as in atomic orbitals, the electrons have energies. Let me just fix this. As in atomic orbitals, the electrons are quantized. So in molecular orbitals also, that means the electrons have energy, or electrons are associated with energy. So just like the electrons that are present in the atomic orbitals, the ones that are close to the nucleus, the ones that are close to the nucleus will have a lower energy. The ones that are further away from the nucleus will have a very high energy. So electrons close to the nucleus, lower energy. And then the electrons farthest from the nucleus, nuclear pull is low, right? Will have the kinetic energy is very high. Degree of freedom is more. Okay, so same concept applies here. So let's do some comparison, more comparison. Okay, so here is a comparison. Let's do this third. The third part is the comparison of atomic orbitals. So comparison of atomic orbitals and the molecular orbitals. What is that? So here is the atomic orbitals. In other words, atomic orbitals, like the way we show it as a valence electrons, basically. So this is the valence bonds. So basically the valence bonds. Okay, so that's the valence bond theory. And then there is the molecular orbitals. So valence bonds are also the atomic orbitals, basically. So these are molecular orbitals. Okay, now we are going to look at, first of all, as we have been talking, I'm condensing things, that bonds are localized. Localized means that we can say for sure that this is a double bond and it is present here. Okay, between the two atoms, whenever the two atoms are bonded, we will see that the bonds are localized. As you can see here, nitrogen, triple bond, stuck, localized, it's not moving, right? Oxygen, double bond, stuck in the middle, it's not moving. So that's what they mean, localization. Lone pairs on the side, in the corner, because there's a repulsion between the lone pairs and the bonded atoms. So that is all about the, coming from the Lewis structures, basically. Lewis structures. Okay, now in the case of the molecular orbitals, what is happening? That the bonds are delocalized. So everything is a resonance. See how interesting? Everything is a resonance. So the bonds are delocalized. So just as you saw, the localized, just as you saw right here was a resonance. Let's see, let's just go back, and you guys had this here. So no, that was not the one. 26, which was the one? Is it here? formal charge. Okay, yeah. So here we covered. So here, this is the resonance. You see, that is the delocalization of the double bonds. So we can say like double bond is present between oxygen and phosphorus. One, this oxygen, that oxygen, that gets a fair chance. Everybody gets to keep double bond, and the rest of them keep the charge. And so we kind of like, that explain that. It all makes sense also. However, in molecular orbital theory, everything is delocalized. So bonds are delocalized throughout the molecules. So there's continuous resonance happening throughout the molecule. All right. Next is bonds created are bonds that are created in the atomic orbitals are formed by the overlap of atoms, atomic orbitals. Okay. So the bonds are formed, or our bonds are created by overlap of atomic orbitals. Okay. And what are those atomic orbitals? Such as when S and S or S and P or SPD, those things. Okay. Or here we include the hybrid orbitals also. Hybrid are the ones there's going to be overlap. Like you made the hybrid orbitals last time. You made these hybrid orbitals. Let's go back and see this. So you made these hybrid orbitals. So, still there's an overlap where you're going to see the probability of finding those two electrons, bonded or paired, and so that's creating that single bond, the sigma bond. And even if it's not the sigma bond, even if it's the sideways overlap, such as in this case, such as in the C2, this is the C2. So even here, you see this hydrogen bond, hydrogen and carbon bond overlapping here, and this is carbon and carbon bond overlapping. So even if it is a hybridized molecule, still, even in the hybridized state, there is an overlap. So overlap of hybrid molecules such as sp, sp2, sp3, sp3d, so sp3d and sp3d2, so sp3d and sp3d2. Okay, so that overlap happens. But in the case of molecular orbitals, they just combine. They don't overlap. All of them mix. So it's the combine. Okay, combine atomic orbitals to form molecular orbitals, and those are such as sigma, sigma star, pi, and pi star. So you see, these are the atomic orbital, molecular orbitals are represented as sigma, sigma star, pi, and pi star, or in other words, bonding and anti-bonding. Okay, so when we say here in the Lewis structures, and even in the even in the hybridized states, I'm going to just put it here, atomic orbitals that are hybridized or just Lewis structures, either way, we see that when there is a single bond is represented as sigma. Okay, and sigma is lateral overlap, flat lateral overlap. But when you create a double bond is made up of one sigma bond and one pi bond. So two bonds in a double bond. Okay, and that one pi bond is actually by the sideways overlap. So we are just overlapping, but producing sigma and pi bonds, sideways overlap. However, in the case of molecular orbitals, what do you see? In the case of molecular orbitals, we see then these molecular orbitals form, whenever these orbitals mix, they form the bonding and anti-bonding. Okay, bonding and anti-bonding interactions. Anti-bonding interactions. Okay, bonding is shown as like this, sigma or pi. So these are bonding, pure, like when they're actually bonding. But sigma star and pi star is anti-bonding. Okay, so this is the difference, anti-bonding. Okay, next is anti-bonding. Okay. Okay, next is, like we talked about, that atomic orbitals, the theory of atomic orbitals, Lewis structures, or hybridization. By that, we use that to predict the shapes. Okay, atomic orbitals are helpful in determining the shapes. So that makes sense. It's not so bad, you know, in determining the shapes of molecules. Internal shape is the electron geometry, and external shape is the molecular geometry. So they predict the shapes based on the number of electrons, number of regions of the electron density. Remember the electron groups we talked about. So the shapes based on electron group density. Okay, next is, what about the atomic orbitals then? Atomic orbitals, so let me just put this here big, shapes, S-H-A-P-E-S. Okay, atomic orbitals, shape, but the molecular orbitals, we determine just to help us, you know, they will help us to understand the arrangement. Just how are they arranged? Arrangement of electrons in molecules. It has nothing to do with shape. Next is, whenever we draw the Lewis structures, so we draw multiple structures to show resonance. Just like we did it earlier, multiple structures in the previous lectures, multiple structures to describe resonance. And yeah, we use the formal charges to prove also. Okay, but we have to draw many structures. Okay, but molecular orbital theory, all of it is resonance. Now that is like totally crazy. Molecular orbitals are a form of resonance. That means the electrons are all the time moving. They are not stationary. So here the resonance is proved by formal charge. And we did that last time, right? And molecular orbitals, so you don't have to prove any, because it's all of it is resonance. Okay, so this is the basic difference and all the postulates of molecular orbital theory. Okay, so bonds are localized. Just let's do a review here. So here the bonds are localized. Here the bonds are delocalized. Here the bonds overlap. Here the bonds combine. When they combine, they form sigma, sigma star, pi, and pi star. Let me write this down here. Sigma, sigma star, and then that one is pi, and this is pi star, Piestar. Okay, so these are these new molecular orbitals. That's their name. Okay, so next is here, their names are sp, sp2, sp3, sp3d, and sp3. So these s and p and d, when they overlap or when they mix with the hybridization, then these are the names. Next is, whenever we make a single bond, we call it sigma, which is fine. This is formed by the lateral overlap. But in a double bond, there is also a pi bond, which is the pi, PIE, which is by the sideways overlap. Okay. Next is the that's the sigma and pi. Okay. But in the molecular orbitals, it is the bonding and the anti-bonding. So either they are bonding or they are not bonding. It's really that simple. Okay. Next is the atomic orbitals. They are helpful in finding the shapes of the molecules. And for those molecules that show resonance, we show them by the multiple structures and we prove them by the formal charge. But here in the molecular orbitals, all of it is a resonance, and it is just the arrangement of the electrons in a molecule, which we are going to study. So what is that arrangement? So remember that we are looking at the wave. So this is the wave nature. This explains, this is now, in other words, tapping into the wave nature of electrons. And these guys were just focused on the particle nature of electrons, particle nature of electrons. And that's it. They stopped there. They totally forgot about the wave nature. So we need to bring in the wave nature also, because that is the reality. They exist as waves. So what is that? First is the third part. This is the third. This is the fourth. LCAO. What is that? LCAO stands for linear. Remember, they are combining. They're not overlapping. They're actually combining, mixing. Linear combination of atomic orbitals to generate molecular orbitals. Okay, molecular orbitals. And in the wave fashion, or tapping into the wave nature, what is that? So wave nature of electrons, wave nature of electrons. Okay. All right. So when we talk about the wave nature of electrons, we need to bring in the nature of the waves also. What is that? So if the two electrons meet in phase, one electron coming in one direction, coming like this, and the other electron is also coming with the same, force, the same intensity, same, like exact same wave. So this is when they meet in sync. So this is the in sync or in phase, meet in phase. When they meet in phase, what is going to happen? Just like, they discovered the structure of the atoms, where they used the waves. So they said, okay, this is going to be a constructive interference. Constructive interference means both of them will have like their waves mix. So this is the constructive interference. Oh, sorry. Interference. FERENCE. Constructive interference. So this means that, what does this mean? This means that there is a higher probability of finding the electrons. Higher probability of finding the electrons. finding the electrons in that region. Okay, so that's one thing. Next is, if you have one electron, remember they are all the time moving. So one electron comes like this, and then another electron comes like this. In the end, you know, it's the pairing of the electron that causes the bonding. Okay, so this is the out of phase interaction, out of phase. So what is that going to lead to? That is going to lead to a destructive interference. That is destructive interference. Are you going to find the electron here? No. These are the regions in space where the electrons can never be found, or they so they are called the nodes. So this is the probability of finding the electrons is equal to 0. Probability of finding the electron is 0. That means then what does it form? Then this is the name of this region is called the nodes. N-O-D-E, node. Very important, where we know actually that the electron is 100% guaranteed, never going to be found. Okay, so now let's look at some of the situations, the graphical representations now. So this is the, after understanding this, now we will, it's becoming a little bit clear now. Graphical representation. Okay, so let's look at an example of hydrogen. Okay, let's look at hydrogen. So these are called a homonuclear. Homo means one type, nuclear, one type, homonuclear diatomic molecule, diatomic. So homo means the nucleus is the same nucleus. Diatomic means two atoms. When they combine together, they form this molecule of hydrogen. So that's one thing. Now, look at this, the energy diagram. Energy diagram is, you here, you're going to make the energy. This is the energy. Now, okay, it's always a good idea, first of all, in these cases to make these, you know, different colors. So you have one hydrogen, lower energy state. So let's just do this here in the middle. Okay, you have one hydrogen and another hydrogen coming close. So this is one hydrogen, 1s1, and this is the another hydrogen of 1s1. So one of them is this color and the other one is this color. Okay, now when they mix together, they come close, and a lower energy state, they combine, right? So two things happen when they come close, then they are going to combine. So they form one and done. These clouds basically, they combine. So here we have this guy, this hydrogen, and the other one is this hydrogen. And here we have hydrogen of one, and this is the next hydrogen. Just basically, this is the combination of the atomic orbitals happens. Combination of atomic orbitals. And what atomic orbitals are there? 1s1 atomic orbitals are 1s1 of one hydrogen plus 1s1 of the other hydrogen. So that's what they will produce. But after the combination, something interesting happens. Once they combine, their energies then begin to add and subtract. Because remember, they are waves, they are moving. So they are not just going to combine and sit there and form like a bond as we see it in the Lewis structures. Lewis structures are also right in their own way. They're not wrong. But when we look at like a little bit more deeply, because if we keep the waves of the electrons in mind, then the molecular orbital theory makes sense. If you're just looking at the electrons from the perspective of the from the perspective of particles, then Lewis structures are right. Okay, so here when their interactions subtract or energies subtract or their energies could add. So when their energies are subtracting, what is happening? So here we see when the energies are subtracting, oh wait, sorry, I did a mistake here. The top one is subtract, the bottom is add. Yeah, adding will lead to a more like a lower energy state. So top is subtract energies and bottom is add. So when the energies are added, then we see this type of bond form where on one side is one hydrogen, other side is another hydrogen, okay? And this is where they were mixing. So this is this cloud and this is the other cloud right here. Okay, so we have hydrogen and hydrogen. Okay, so two hydrogens basically all mixed together, lower than the initial ones. So this is a combined state. So that combined state is the bonding molecular orbitals. Okay, bonding. This is the bonding molecular orbitals are formed. Okay, and these bonding molecular orbitals will have a lower energy. That is why they are lower. You can, as you can see, they go down. Okay, and when these basically these are this is a wave. This is a wave. So that means when these are waves are meeting in phase, only then you will have bonding molecular orbitals. Okay. So what type of bonding molecular orbital is this? In this case, hydrogen, and hydrogen is, yes, it is a single bond, but this is called the sigma bond is formed. It is a sigma is the molecular orbital. Okay. But what happens if they are meeting out of phase? Remember, they are waves, they are moving, they can also meet out of phase. Then you have one side fine. Hydrogen is still going to be close to the other hydrogen, but they are not going to interact. So this guy will remain still close to the other hydrogen. This guy, the two hydrogens are still going to be staying close to each other, but they're not going to bond. So in this case, what is this then? This empty space is called the node. Remember, node is always formed when there is a destructive interference, when they do not meet, when the waves are meeting out of phase. So that empty space is called a node. And the molecular orbital is called the anti-bonding molecular orbital. Okay, and the way you are going to represent it is sigma star. Okay, sigma, it is still sigma, but star is, that is just to show that it's not bonding. So this is out of phase mixing. Okay, so that's the deal with hydrogen. That is when there are s orbitals are mixing. When s orbitals are mixing, then this is what you get. All right, clear? So this is part one. Next, let's look at the graphical representation of p orbitals. P orbitals. What happens when the p orbitals mix? So here, oh God, it's an important call, but Why they have to call it this time? Sorry about that, guys. It's very strange. Okay, anyways, so p orbitals, okay? P orbitals, now p orbitals, remember that p orbitals are px, py, and pz. So how do they look like? They all three of them in 3 dimension, all three of them in 3 dimension are like this. So this is the x, this is the z, and this is the y. And so here we have the px is this, px, py is this, the top one, okay? And pz is this. All in one, place. So pz is diagonally, okay? So the three of them. So how does this happen here? Now let's look at the px orbitals. So px orbitals, when they meet in phase and out of phase. In phase, yeah. px when they meet in phase. So let's do this. Out of phase is more energy. Yeah, out of phase. So out of phase. And we will look at the in phase. Okay, and so here is this energy of the increase in the energy. Energy diagrams. Okay, so here we see when they meet out of phase. So this is one end and this is the other end. In phase, again, one end and then another end. So how do you show these phases? Colors. So when they meet out of phase, so out of phase, in phase, you see the greens and greens looking at each other. The out of phase is when the greens and greens are away from each other. And, oh no, sorry, I made the mistake here, this one. So green and green, yeah. So this would be, sorry. So they are not going to interact at all. So this green and green are talking to each other. Here, green and green are away. You see that? So in this case, we see this, that green and purple will not talk. Green and purple are not talking. Here, the green and green will talk. And then when they switch, the purple and purple or pink and pink will talk. So when they meet, this one is out of phase and the first one is in phase. When they mix, then what do they form? This guy forms the little bit of the pink here, a little bit of the pink here, but a lot of, sorry, right here. Okay. When they mix, one side is like that, and the other side is like that. Okay, so here we have the green is this, and another green is here. The other one is big pink is here, and a small pink is here. So different colors don't even meet. But this one here forms like a candy, like a huge big candy. And what do you see here? We see the big portion in the middle is the green portion, because that is one that mixed. They talked to each other. They came in phase. And this guy, these two little ones were away. So yeah, that's fine. So a lot of mixing has happened in the first case, in the bottom case, lower energy state. Okay, so lower energy state, this is going to create a sigma p x molecular orbital. Okay, so this is lower energy state, lower energy, and they are forming, this is a constructive interference, constructive like interference of waves. And that is why they are forming the bonding. So these are the bonding molecular orbitals. Okay, but the top one is the destructive interference. So they're really not even mixing. They are close to each other, but they are not mixing. Interference, or rather combining. Okay, so that's higher energy state. Higher energy state is that they are unstable. So they will be anti-bonding. So instead of, they're not bonding, but they are close, yeah, but at the same time, they are repelling each other also. So how would you show this? This is shown as the sigma star molecular orbital. So this is sigma star anti-bonding, and this is sigma, which is bonding. Okay. So this is one thing. But what happens if you have PY mixing? PY, or the same thing applies to PZ. So that is when there is a sideways overlap. This is when this is basically lateral overlap. This is lateral. Lateral is PX is always going to be flat, lateral overlap, or basically lateral combining, you know. And this is the lateral overlap over internuclear distance. Internuclear distance. Internuclear means between the two nucleus. Okay, so internuclear axis, sorry, not the distance, internuclear axis. So if we take like a rod and we pass it through the nucleus of the two atoms, you know, so we are now looking at it, what's happening on that axis. So lateral overlap is flat overlap, but there is a sideways overlap also. So what is happening in the sideways overlap? Sideways overlap leads to pi bonding. So what do the orbitals look like? So here is the energy. Okay, and here is the energy, and then we have the this. Okay, now here we have out of phase, top one. The bottom one is in phase. So you see the colors are on the same side. So out of phase, the different colors on the opposite side. The in phase, same side. So let me write this down. This is in phase, this is out of phase. Out of phase is always going to be a higher energy state. In phase is always going to be a lower energy state. So in phase, okay, now in this, what is happening? How do they interact in this case? They bend actually. So just imagine that, let me get this other color. Just imagine there is a like let's see, like a glass. Okay, like a glass. So if you had like a glass table, how would they look like on a glass table? So this is a flat surface of the glass, and let's say this is also another surface of the glass, you know, so the two glass pieces. So how are they going to look like? Like they will be squished in the sense like this one is going to point away, and then the bottom side is also from here, from the bottom side is pointing away. This one is also pointing away, and this one is like complete repulsion basically. So like that. So like that. Okay, so we have here now the pink on the top, which is fine, but here the pink is at the bottom, so no combination. And same is the case, this one is like, it's just like, you know, like it's been like, what do you call this? Distorted, basically. So here we will have the pi star, and you will write it as pi py. So this is the anti-bonding. There is no bonding happening, anti-bonding. And in this case, there are actually two nodal planes. One is a vertical nodal plane where the electrons are never going to be found. So vertical nodal plane. Okay, vertical nodal plane, electrons never found. And horizontal nodal plane also. In this horizontal part, the electrons are never going to be found. But yeah, even though the electrons are not mixing, they're still going to be found in that region of space. So, that's why they're electron clouds in the end. But what happens in this case? In this case, if they are meeting in sync, then what happens? So here, in this case, we see that they mix and they form like, in other words, they combine actually, not even mix, combine. And this other one is like, oh. So here is the bottom part, like that. Okay, so where is the nodal plane here? The nodal plane is flat. So like a table again. So on the table, this is the table, the top part and the bottom part. So on the top part, you're going to find the pink portion, the pink color, and the bottom one, you're going to find the green one. All right. And what do you see? Okay. Horizontal nodal plane. And so this is the pi p y, and that is the bonding molecular orbital, and this is the horizontal nodal plane. Okay, horizontal nodal plane. And so these are the pi py's. They look like that, bonding. So that's the sideways. And the same applies to pz. Okay. So with that said, how many atomic orbitals are there? So remember, we talked about that atomic orbitals and the molecular orbitals are the same. So, but a little bit more for the, how would you show? So for every phase, there is an out of phase also. So a total of total molecular orbitals. So you look at this here, total molecular orbitals. So if, look here, if there are, there is a sigma bond, then there's going to be sigma star also. Keep that in mind. If there is a pi bond that relates to px, then there is going to be pi star px. If there is a pi py, then there is a pi star py. If there is a pi pz, then there is a pi star pz. So you see that for the s orbitals, this is the s orbitals, there are two. So these are the atomic orbitals, just the s, and these are just the p's. Okay, so this is just the p's, px, py, and pz. But molecular orbitals are what? How many? 1, 2, 3, 4, 5, and 6. So there is only one atomic orbital, but there are two molecular orbitals that relates to SS bonding. There are three. This is the atomic orbital. There are three atomic orbitals that is coming from three p's. Remember, p has got three orbitals where you will find these guys like that. But atomic orbitals, there are 6 as shown above. So for every bonding, there is an anti-bonding also. So that's why. So you see that? That's the difference. Okay, now comes the important concept of bond order, and then we will do the examples, and the rest is so easy. It's not hard. So all you need to do is create a template. I know you guys have the exam also coming up, but you just have to create a template. Okay, bond order, and then you can just use the template to do these problems. So here, bond order. So this one is the 6. Okay, bond order is BO. Now, bond order relates to bond length. Bond order relates to bond length. Let me just write this here. Bond length. Bond length is BL. Bond strength, the strength of the bond, right? In the end, they're molecules. So it is BS. And then, which is the other one? Bond length, and then bond energies. Bond energy is BE. Okay, so, and then is the bond order is BO. So how are all these related? Bond order is related to bond length. Bond length is related to bond energy. And bond energy is related to bond strength. Okay, so these are like they're all related to each other. And we will see this. Let me just move this here. So what is that? What is the meaning of this and how do they relate? Okay. So some rules here, write down these rules. Let me write this in red. So when bond order is 0, then no bonds are formed. No bonds are formed when bond order is 0. When bond order is 1, then what is formed? Single bond is formed. When bond order is 2, then double bond is formed. Simple, right? So write this down. Double bond is formed. When bond order is 3, then triple bond is formed. Okay, so that's one thing. Whatever you will be calculating the bond orders, and we will confirm whether the structure is right or not. Okay, next is another important relationship is that when the relationship between bond order, when the bond order goes up, single bond, right? Then when the bond order goes up, then the bond strength also goes up. In other words, bond order is directly proportional to the bond strength. Bond strength is directly proportional to bond order. So if the bond order increases, the bond strength, the strength of the bond also increases. And when the bond order goes down, then the strength of the bonds also go down. One piece. Next is when bond length is one second. Bond length is inversely proportional to bond order. So bond length is inversely proportional to bond order. So this means that when bond order goes up, the bond length goes down. When the bond order goes down, then the bond length goes up. Okay, so one piece. Next is the bond energy. Bond order and bond energy are directly related. So this means that when bond order increases, the bond energies also increase. And when bond order goes down, then the bond energies also go down. All right, but there are some exceptions here. Always chemistry is, that's why it's so hard. Yeah, it depends on the atoms also. Depends upon the atoms. So yeah, it's all by case, you know, like if they are feasible, like B2, like example, boron reacting to itself versus fluorine reacting to itself. So here, the bond order, so this is bond order is low. That means this molecule is not going to form. B2, not going to, no bond possible. Whereas here, the single bond, one single bond is present. Okay, so that means the bond order is 0. So bond energy, there's no bond energy is equal to 0. Okay, here the bond, there's going to be some bond order. Bond order is 1, so bond energy will have some value. Okay, some value. All right. So remember that more negative the bond energy is, the more stable the bond is going to be. All right. Now, here is what you're going to do is, sorry. So this is unstable bond. This is unstable. Even if you force to make the bond, this is unstable bond. And this one is a stable bond, very stable bond with fluorine and fluorine. Okay, very stable bond. And so just keep this in mind, that single bond versus the double bond versus the triple bond. So here, with respect to the bond length is highest in the single bond. So bond length is highest for the single bond, and bond length is the lowest for the double bond. The length of the bond. And with that said comes the strength of the bond too. Here is the single bond, double bond, and triple bond. So single bonds, the strength of the bond is the weakest in the single bond, not very strong bond. You can easily break this single bond. So the strength is weakest, but the bond strength of a triple bond is very high, very strong bond. So bond strength is highest, lowest for the triple bond. And here the bond strength is the lowest, and here is the highest. So keep that in mind. Okay, now what you're going to do is make a template. Now we are going to create the energy diagram. So for that, create a template. And you should have these notes for it. So a template. Template for energy diagrams. Okay, so luckily you guys have a very, like, since this is just an introductory beginning part, you know, so you will have like a very simple template which you can just follow and go from there. Okay, so here is this period 2. Period 2. In period 2, we have what? We have boron, we have carbon, and we have nitrogen. And then comes oxygen, then comes fluorine, and then comes neon. Okay, now here, divide this because there's a difference here. Divide this. All right, so why is there a difference? Because it's this side is the two S and P mixing. So as you go from left to right, so you're basically moving from left to right, as you go from the left to right, what increases? The effective nuclear charge is increasing. Okay, so when the effective nuclear charge increases, the size goes down, the size decreases. Okay, so going from left to right in the periodic table. So you would see the increase in charge. And here we have the 2s and 2p mixing happening. So here we have the, sorry, I'll just remove this. So here 2s and 2p mixing. All right, now let's start doing this. Okay. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. Just give me 1 minute. 1, 2, 3, 4, 5, and then so I need to make this. Okay. All right. So sigma 2s is this. After that comes the sigma star 2s. Sigma 2s, sigma star 2s. Next. Okay. After that comes, this is the mixing. Then comes the pi 2p. Okay. And that is the y. And this guy over here is the pi 2p z. Okay. Then comes pi 2p x on top. And then comes the pi star. And then here. So this is the pi star 2p y. And this is pi star, that is the anti-bonding, 2p z. And then comes the pi star 2p x. Okay. So you see this, this is the way you will arrange them first. It's easy. This so if the combination is between boron and boron, carbon and carbon, nitrogen and nitrogen, you're going to use this template. Okay, so B2, carbon and nitrogen. Just put this here. B2, carbon and carbon, C2, and nitrogen, N2. You're going to use this. The next one is for oxygen and oxygen, fluorine and fluorine, and neon and neon. If they were mixing, then what is formed? How does this look like? So sigma 2s is the same, sigma 2s, and then comes the sigma star 2s is above that. Then comes the sigma 2p. You see it? And that's the sigma 2px. Then comes the oh wait 1 second here. There's a little bit mistake here. This would not be pi, px here on the left hand side, please, where we did the boron, carbon and nitrogen. This is actually sigma. That's a lateral overlap. So that's a typo error. So fix this over here, everyone. Because there is a difference between the sigma 2px and sigma 2p. So in the first case on the left hand side, between boron, carbon and nitrogen, sigma, the px is mixed later. But with oxygen, fluorine and nitrogen, because of the nuclear pull, the px is mixed first, and that forms the sigma bond. So sigma bond is always lateral overlap. After that comes the pi 2py and pi 2pz. And that is the bonding. Then comes the anti-bonding, which is pi star 2py and pi star 2py. And then comes the sigma star. So here also this would be, again, how could I do this thing? Sigma here. So just pay attention to the sigma 2px. Okay. sigma 2px, this is sigma 2px, and this is sigma 2px. So it's sigma 2px is so high up. This is all energy. This is the increase in the energy. Remember, we said that these molecular orbitals are also quantized. So this is increase in the energy. So that means that it's never going to happen. That's what it means. That's why it's so high up in the energy. Or even if it happens, it's very temporary. Okay, now let's start the real stuff, which is drawing these energy diagrams. So now we will see the energy diagram of oxygen. So this is the 8. Okay, why is oxygen paramagnetic? So now we can see this from these energy diagram. Why is oxygen paramagnetic? Paramagnetic. Now we can see this. Okay, so look at this oxygen, the energy diagram of oxygen. Okay, energy diagram of oxygen. So we see here that oxygen is 8, 1s2, 2s2, 2p, 4. Okay, and so the orbital diagram is 2s2 and 2p4 looks like this. So we will still look at the valence electrons. So 1, 2, and then 2p4 is here. So here we see 2 unpaired electrons, and then the other oxygen comes. Another oxygen comes with its 8 electrons, 1s2, 2s2, and 2p4 also has the same scenario. And so, yeah, technically you should see these two guys, these are the lone pairs, and these two guys are going to overlap. This and this overlap, this and this overlap. So that's where we see a double bond formed. Okay, so let's look at the total, first of all, total electrons that are involved in the formation of these bonds, or total valence electrons, basically. Total valence electrons. So 1, 2, 3, 4, 5, 6, 6 coming from 1, and the other one also has total valence electrons of 6. So now in the molecular orbitals, we are going to place these 12 electrons. So very important that you get this number right. If you don't have this number right, then it's a total mess. All right. Next is energy diagram. So draw the energy, like this here. Now, look at the template. Look at the template for oxygen above, and just copy it down. Okay, just copy it down. That's all you need to do. So for oxygen, oxygen is the sigma 2p comes first. So all we are going to place, this is 2s, this is 2s, this is 2s, this is 2p, 2p. We're just going to work on these, not the initial ones. So here is the 2s. So here is one oxygen. So we will just put this here, sigma. I'm going to just bring this. So just put that template. So this is the sigma 2s, sigma star 2s. Then comes the sigma 2p, sigma 2px. Then comes the pi 2p. One is z and one is y. So let's not just put the, you understand, so I don't want to put the x's. So pi 2p, and the other one is also pi 2p. Then comes the pi star 2p. Pi star 2p means the antibonding 2p, and this is 2p. Okay, and then comes the sigma star 2p. That's the x. Okay, and now how many electrons we have? We have to place, just simply place 12 electrons, okay, like in atomic orbitals. So 1, look here, everyone. 1, 2, 3, 4, 5, 6, 7, 8. So this is singly occupy here. Singly occupy first, next, pair them with opposite spin. So it's, same way you do it with the atomic orbitals. Okay, so we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. All 12 have been accounted for. Okay, but that explains they are not paired. They are in different orbitals. You see that? So Lewis structure, back to square one, doesn't show that. Lewis structure shows, yeah, all these 12 of them are here. Where is it? Where did it go? The Lewis structure shows all 12 of them are here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And looks all of them are paired, but it doesn't explain the paramagnetic character. But if you look at the molecular orbital diagram of oxygen, you are going to see that they are, 2 of them are actually unpaired. So that is the, these are the unpaired electrons that cause paramagnetism. That explains it. Okay, clear, guys? Okay, there's something else we forgot to do regarding the bond order, the main formula for the bond order. So let us just still confirm, like, he doesn't, like, it's okay. Somebody can say, oh, whatever, these theories, scientists, they think very deeply. They can come up with a theory. You always need to prove. How? Well, like, does it make sense? I mean, there has to be a double bond. We don't care. There has to be a double bond. We don't care about paramagnetism. We only care about a double bond. Where is it? It is there. We know it is there. So that's where the bond order proves that. So there's a formula for the bond order, which is total number of bonding electrons. You count the total number of bonding electrons minus the number of anti-bonding electrons, divided by 2. Okay, so let's see. Can we get that? So what is a bond order? Bond order in oxygen, number of bonding electrons. Which ones are the bonding electrons? The bonding electrons are 2s, sigma 2s, then the sigma 2p, then the pi 2s and 2p, like pi 2p's. So there are, like, how many do we have? So we have 1, 2, 3, 4, 5, 6, 7, 8. 8 of them are the sigma, like bonding, sorry. 8 of them are bonding and 4 are non-bonding. So 8 electrons are bonding minus 4 are non-bonding. You divide that whole thing by 2, and what do you get? You get 4 divided by 2 is equal to 2. So when the bond order is 2, remember right here, when the bond order is 2, what is that? It's a double bond. So through the molecular orbital theory, yes, you can confirm. Yes, fine. They don't want to make the whole community mad because we all design structures, Lewis structures, that is proving the shapes of the molecules, and here you're defining it. Doesn't make sense. So you need to agree to that. Yes, the bond order proves that oxygen and oxygen will have a double bond. Okay. Oxygen and oxygen will have a double bond. And that is explained through the bond order. Proves it. Bond order proves it. Okay. So that means if somebody asks you now, is this molecule paramagnetic or diamagnetic? Yes, this is paramagnetic. Paramagnetic because it has two. Paramagnetic because it has two, wait a minute, two unpaired electrons. Okay, I need to correct this here. Just now we proved it, but somewhere I have this here. In oxygen, there is one or two. Just fix that one here because we just now saw that there is one or more unpaired electrons. Okay, so that's just one part. Okay, so that's the type of questions we will ask you. Draw the molecular orbital, draw this molecular orbital diagrams and show what is the bond order. And second thing is that we are going to write the electronic configuration. So how would you write the electronic configuration? Electronic configuration is now sigma 2s brackets sigma star 2s brackets closed, then comes the sigma 2p brackets, then comes the pi 2p, and then there's another pi 2p. Remember that this is the x, this is the y, and this is the z. Then comes after that pi star, then pi star 2p y brackets closed, or you can put them all in same, or you can also put it like 4p, that's also fine, comma, and then 2p z pi star, that's the same energy state, pi star 2p z, then comes the, so that's all. Oh, sorry, this is 1 and 1. So this would be 1 and this is 1. 1 here and 1 here. That's all. That's how you will show. Okay, and if you count it, it will all come out to be 12 electrons. All right, guys. Now let's look at for nitrogen also before we wrap up. So this is one example. Why oxygen is paramagnetic and why nitrogen is diamagnetic. So same story, you are going to use the template. So use the template for nitrogen shown above. Okay, so same thing, the energy diagram is, here is the increase in energy, and we will, next thing is, we will have for the nitrogen is, one nitrogen has 7 electrons, the other 7 electrons, it's 1s2, 2s2, 2p3, the other one is 1s2, 2s2, and 2p3. So 2s2 and 2p3, 2s2 and 2p3. So this is how it looks. 1, 2, 1, 2, 3, 1, 2, 1, 2, 3. And you see that these are overlapping. So we have nitrogen and other nitrogen in triple bond, and these 2 electrons right here. Okay, so that's fine. But a total valence electrons, that's the most important number. So total valence electrons are, these are the valence electrons, 2s2 and 2p3, 2s2 and 2p3. So this is 3 and 3, 6 and 10. So we are looking at 10 valence electrons. Okay, so now let's start putting it. So first is the sigma 2s then comes the sigma star 2s, and then comes the because this is the pi 2p, and then comes the pi star 2p, and then comes the, oh wait, 1 second, it's not a pi star. Just look at this. Here is, yeah, then comes pi to p, and then sigma 2p, and then comes the pi 2p pi star, and then comes the sigma star 2p. So this is the x, this is the y and z, this is the x, this is the y and z, and that's the s. Okay, so we have 10 electrons now. So 1, 2, 3, 4. Now pay attention. 5, first singly occupied. 6, next paired. 7, 8, 9, and 10. So all electrons are paired. So when all the electrons are paired, what's happening here? Therefore, repulsion in the magnetic field. The repulsion in magnetic field. All right. So let's prove the bond order. What is the bond order? So bond order is number of bonding electrons minus the number of anti-bonding electrons, divide that by 2. So bonding electrons are which ones? So this is 2 from here, then 2 into 4 from here, and 5, 6, 6 from here. So total is 1, 2, 3, 4, 5, 6, 7, 8. 8. 8 are bonding. And how many are non-bonding? The non-bondings are these ones. Okay, so there are only 2 non-bonded. Divide by 2. So you get here 8 minus 2 is 6. 6 divided by 2 is 3. So that shows the formation of triple bond. Okay, and so same thing, there are three, so that's a triple bond, and there is a no, so that is the diamagnetic character. No unpaired electrons. So no unpaired electrons. So this is diamagnetic. Okay. And then if somebody asks you to write the electronic configuration, you know, of the last shell, basically. So it is going to be sigma 2s brackets closed, sigma star 2s brackets closed, then comes the pi. There are actually 4. So you can write down all them together. 4 pi, you know, py and z, py. What am I doing here? Yeah, that's right. Okay, for py and z, and then comes the sigma 2px, sigma 2px. All right. So if you count them, you have 2 plus 2, 4, 4 plus 4, 8, 8 plus 2, 10. All 10 electrons have been accounted for. Okay, so this is how, you know, you will do, but just pay attention to a few things, that which one will be a stronger bond. So just look at this. Which one is a stronger bond? Let me just finish this. Which one is a stronger bond? Which is stronger? you have nitrogen versus oxygen. So the bond order of nitrogen is 3, which is more than the bond order of oxygen, which is 2. So just based on the bond order, you will see the bond strength of nitrogen is more. Nitrogen is more in bond strength than oxygen. Bond length of nitrogen is less than the bond length of oxygen. Okay, and bond energy of nitrogen is more than the bond energy of oxygen. So it all depends. So look at so this is all these questions are based on the look at the relationships that when the bond length increases or bond length is directly proportional to the bond order. Everything is related to bond order. Bond order is directly proportional to bond strength and bond energy. So bond energy and bond order is directly proportional to bond strength. But bond order is opposite with the as far as the bond length is inversely related to bond length. So the more the bond order, the less the bond length is. Bond order low, bond length higher, and so forth. Okay, guys. So, that's just one thing. And if there is a charge, then just add an extra electron, I mean, I can. So that's just, that finishes this chapter right here. And if you guys have any questions, you can ask. But, this is a very interesting concept. So, all right, guys. I know you guys have a test also on this on Monday, but, so we will not be having our class, no lecture, but you guys will come to the, so don't come to the, don't come to the class on Monday. It will be in the Zoom. All right. You're allowed to take the notes and everything, but, we just have to, I understand that it might be a lot, but, you're allowed to use the notes on the exam. So if you are doing the extra credits and the homework, you should be okay. Okay. I know it's a lot of work, but, it's just, just a little bit more time. Okay. And you'll be fine. All right, guys. Okay. I'm ending the meeting now.